So now that you know how to write equations for polynomials, why don't we extend that a little bit? There's actually a little bit more going on than we've just looked at, although what we have looked at is still 100% true. I just want to do some extensions with you. Now, if you look at the three polynomial graphs over here, they're not the first graphs that you've seen, but if you look at them, there's something kind of the same about them and, quite honestly, something kind of different. Essentially based on their equations. Like this first equation, the one that goes with graph A. You see, that equation, that's the parent equation. It's the parent equation because it's kind of where all of these other equations originate from. We could also say that the graph is the parent graph. And what we see on the parent graph is hopefully what we expect to see. That is some roots that go with these factors, like x plus 3 goes with negative 3, and x minus 2 goes with 2, and x plus 1 goes with negative 1. So we have the parent graph. But how about B? Equation B, graph B. It seems to be the same equation, but it's got a coefficient. It's got a coefficient that has changed the shape of the graph. Yeah, do you remember if the coefficient is less than 1, the graph is going to look compressed. It's going to look like somebody pushed on the graph. But even though the graph is compressed, let's make sure we make note that graph B is compressed. The A value is less than 1. Even though it's compressed, it still seems to have a lot of the similar features that we had on our first graph. That is the roots, like how x plus 3 goes with negative 3 and x minus 2 goes with 2 and x plus 1 goes with negative 1. So it's related, but yet it's different. It's been compressed. And how about this graph C, equation C? Looks like the same equation, but it's got this coefficient. And this coefficient actually is greater than 1. That's why the graph looks like it's been stretched. That's why the graph looks like it's been stretched. The coefficient is greater than 1. Same thing. It's got the same roots. In fact, do you get the idea now that the roots are what tie all of these graphs together? Yeah, they all have the same roots. And we'll put that in the overlapping region here. So the whole point is that these polynomial equations and these polynomial graphs, yeah, they're very similar. Still, though, they're different mainly by their exact stretch or compress that is all related back to the parent graph, which is where each of these graphs came from. Actually, maybe we should have the arrow pointing the other way. So what we can do now is we can actually think about writing some equations for polynomials that have been transformed. To be transformed means that they might have been stretched or compressed. However, to write those equations, what we're going to have to do is we're going to have to notice some things from each graph. We're going to have to notice the important parts so that we can end up with this transformed equation. So perhaps the most important thing to notice from any graph is still the roots. Yep, the roots. It's where a lot of this begins, and it's still where a lot of this ends. So I've got negative 2, negative 1, and 2. And 100% we're going to use those roots. We're going to use those roots to write our factors. But there's some other things on this graph, aren't there? Yeah, it looks like that there is a point that is given. A point. It's something to notice. And ultimately what we're going to end up doing is using that point to help us come up with the actual stretch or compress. By the way, there's also a y-intercept that's shown. The y-intercept is going to end up being a checkpoint. So you'll notice that I'm not really recording that one, but I am aware that there's a y-intercept. How about the behaviors of the graph? That is the end behavior. It's something to notice. Don't forget about that end behavior idea. So we'll notice that and say that the graph is going up to the right and down to the left. It's just something that we're going to notice. Perhaps that might come into play at some point. So we need to write an equation. Okay, now you haven't forgotten, right? This is what we did yesterday. Whenever you write an equation, you always start with the factors. And the factors come from the roots. And so, yep, those roots still are the most important part. -2 is a root. X plus 2 is a factor. -1 is a root. X plus 1 is a factor. And 2 is a root, so x minus 2 is a factor. Now, here's the thing. We now know that there's the possibility for a stretch or compress value. That is, there is a chance for a coefficient of a. So we're going to leave a space for the letter a, and ultimately what we're going to do is end up solving for a. So how are we going to solve for a? Well, we're going to plug in a point. We're going to plug in the point that we noticed in this problem, 1 and -12. Now, anytime you plug a point into an algebra equation, you always plug the x in for x, but first you can see the y is being plugged in for y. So -12 is being plugged in for y. And check this out. There's actually 3 places where you're going to plug in the x value. The x value of 1, of course, but there's 3 places where I plug in 1 for x. Little different kind of equation. Yeah, to solve this equation, I'm going to actually do each of these little parentheses. So 1 plus 2 is 3, 1 plus 1 is 2, and 1 minus 2 is -1. So I do all those little mini parentheses, and, well, yep, I'm on my way to solve for a. I'm solving for a. I hope you multiply all these numbers together and get -6. We'll put the a with it, so we have -6a. And ultimately, that means a equals 2. Now, since a equals 2, I'm able to kind of revise my equation to be 2 times each of these factors. I'm able to plug 2 back in for the letter a. But the equation, it's not really in standard form, is it? Yeah, all these equations need to be multiplied out. It's kind of a little bit of a bugger, but it's just something we got to do. So we're going to multiply out the x plus 2, x plus 1. Now when you do that, you get x squared. 2x and 1x make 3x, and finally 2. But I still have this x minus 2 that's left over here, and that x minus 2 also needs to be part of the expanding or distributing. Now, notice I haven't done anything with my coefficient of 2. That's right, I'm going to keep that. I'm going to keep that coefficient until the last step. But I do need to continue to expand all this. I feel like I'm going to get like an x cubed, a minus 2x squared. I feel like I'm going to get a 3x squared and a minus 6x. And then we still need to multiply this 2 to give me a 2x and a minus 4. I'm kind of squeezing this in here because we're going to combine like terms eventually to be x cubed plus x squared minus 4x minus 4. Okay, so I have my simplified equation with a 2 in front of it. That's right, this 2 is now going to distribute into and onto each of these terms so I can finally get my standard form equation. 2x cubed, 2x squared, minus 8x, minus 8x. And that's your polynomial equation. Now, if you wanted to, you could check that equation with Desmos. As we've done some other times, I'm going to say you could do that. And you will see that the equation, the graph that is, looks exactly like this graph. Note that the graph is also going to have the end behavior that we expect it to have. It's going to go up to the right and down to the left. That is, of course, because we have the positive leading coefficient as well as the negative or odd degree. So that's all good also. And there's one more thing that's pretty neat about this answer. It's the y-intercept. That's right, the y-intercept, remember that's always the last number, and it's -8. And on the graph it's -8. So I'm feeling pretty good about this answer. Everything is matching up. It is correct. It's time for you to try a problem. I don't have all the steps down and all the spaces for you to fill in, but are you able to look at this graph and start to take the parts that you need to write the equation? Go ahead. What are you waiting for? You want to try the problem. Push pause on the video and see if you can write the equation. You should be noticing the roots, right? In fact, it wouldn't be a bad idea if you're taking those roots and you're already creating your factors. You know that that's what's going to happen. So, yep, you can definitely start with those factors. Make sure you wrote them correctly. X plus 2, x minus 5, x minus 7. This is all about the a value. So we now need to put the a variable into the equation. That means you're going to be solving for it. When you plug in this point, you're going to plug in the point. So that means you're plugging -40 in for y. And it's pretty fun. You're actually plugging 3 in for x, and for x. You're actually plugging 3 in for all the x's. Keep in mind that the goal here is to solve for a. So you're kind of working out the equation. You're doing all these little parentheses. You're solving the equation. So I really want to figure out what 5, -2, and -4 equals. And that all shakes out to be 40. 40a. So how about we write it that way? We'll write 40a, which means a equals -1. A equals -1. Okay? So what do I do with that? Well, I gotta put that back in. I gotta put that number back into my equation. That is, I gotta put -1 back in for a. But I still have x plus 2, x minus 5, x minus 7. I still have all of those parts, which means now you have to multiply them all together. Yeah, you have to multiply them all together. Usually recommend you just take 2 of them at a time. Don't forget about your -1 out here, but you'll notice that I'm not doing anything with that yet. So I'm going to get an x squared, a minus 5x, and a plus 2x. So that's x squared minus 3x, and then minus 10. Still have my x minus 7 here. Keep your -1 out front, but you're going to multiply all this stuff together. We get x cubed, we get minus 7x squared, we get minus 3x squared, we get 21x, minus 10x, and plus 70. So it's going to be x cubed minus 10x squared plus 11x plus 70. Now I went ahead and just kind of simplified that, but there's still a negative 1 in front. So that negative 1 is going to distribute. It's going to distribute onto all of these terms. So I really end up with just negative x cubed, positive 10x squared, negative 11x, and negative 70. What do you think about that equation? Does it match the graph? Well, we didn't say anything about the end behavior, but if you think about it, the graph is going down to the right. If it's going down to the right, it better have a negative leading coefficient, which it does. I also noticed that it's going up to the opposite direction to the left, which fits perfectly with my odd degree. And finally, yep, the y-intercept. Pretty cool. Negative 70 is the y-intercept, and that looks perfect on the graph, which is a great double check that all is correct. So I have negative x cubed plus 10x squared minus 11x minus 70. Let's do a couple more just kind of thinker questions as we try to close up things with writing polynomial functions. What if I wanted to write a 5th degree function that has these roots? Now you say, well, I don't have enough information. Yeah, you got to kind of remember some things. For example, if you have an imaginary root, that really meant that you had the pair of roots. Now I'm pretty sure that plus or minus 2i counts as 2 roots. This looks like it's a 3rd root, but it says 5th degree. Well, 5th degree means that I should actually have 5 roots. So the only other choice is to say, well, then I guess this 0 has to have a multiplicity of 3. It's the only other thing that I can do so that I end up with a 5th degree. So all those zeros are going to give me an x cubed, and then my 2i, or that is my plus or minus 2i, remember, those always come from an x squared plus where the 2i came from, and the 2i had to come from a 4. So I end up with, when multiplying these together, x to the 5th and 4x cubed. 5th degree. It's got it to the 5th degree. What do we got here? A 4th degree. A 4th degree. Now remember, 4th degree means that there's got to be 4 roots. It looks kind of like I only have 1 root, 2 roots, until I go a little further. Remember, whenever you have a square root, it always is a plus or minus. It doesn't have to be imaginary. So if I have one, I have to have the other. And even if I have a square root in this form, there's always a plus or minus. So there's my 4 roots. My 2 other roots, in fact, really all 4 of them. I don't think we need to write an equation for that problem. It was just kind of there to make you think. And that's what the homework's for also, to get you to think and to practice a little bit more with these polynomial, more advanced polynomial equations.